Hello students. In the last video we had discussed about bounded sets, bounded above sets, bounded below sets and bounded sets. So let us continue this discussion. I had also given some idea about the least upper bound and the greatest lower bound. So I begin exactly from where we left in the last video. This diagram, I was explaining this diagram. So this is the set A equal to 1, 2, 3, 5, which is a finite set. For this set, 1 is a lower bound, 0 is a lower bound, anything less than 1 is a lower bound, that I had explained. Anything less than 1 is a lower bound, anything greater than 5 is a upper bound, right? And also we had seen that out of all these lower bounds, 1 is the greatest, and out of all these upper bounds, 5 is the smallest or the least, right? So 1 is the greatest of all the lower bounds and 5 is the smallest of all the upper bounds, right? So we define formally what is the least upper bound and what is the greatest lower bound. So least upper bound, let S be a subset of R, be any bounded above set, then U belongs to R is said to be least upper bound of S if it satisfies the following two conditions. So what are the conditions? First condition is U should be an upper bound. U is an upper bound of S, that is X less than or equal to U for every X inside S. And second condition is if V is any other upper bound of S, then U should be less than or equal to B, because U is the least upper bound, smallest of all the upper bounds. So if V is any upper bound of S, then the relation between U and V should be U less than or equal to V, right? That is, U is the smallest of all the upper bounds. Okay, so we will show that the least upper bound of a bounded above set is unique. There is one and only one least upper bound. Okay, so we can always say the least upper bound instead of saying a least upper bound, because there is only one least upper bound. Okay, so this is the exercise. Least upper bound of a bounded above set is unique. Okay, so how to show this? It's very simple, just arguments based on the definition. So let S be a bounded above set and let U and V be two least upper bounds. Okay, suppose that U and V are two least upper bounds of S. Then you observe that taking U as the least upper bound, we have already taken U as the least upper bound. So and V is also a least upper bound, we had supposed. So first of all, V is an upper bound, right? So V is any upper bound and U is the least upper bound. U is a least upper bound. Then what is the relation between U and V? As per the earlier definition, U should be less than or equal to V. Again, since we have supposed that V is also a least upper bound, so V is least upper bound and U is an upper bound of S. So relation between V and U should be V less than or equal to U, right? So from 1 and 2, we should have what? U less than or equal to V, V less than or equal to U. So that will imply that U is equal to V. Only this case is possible. Okay. If both 1 and 2 are to be true, then only possibility is U should be equal to V, right? So least upper bound of a bounded above set is unique. So similarly, let us define what is greatest lower bound or infimum of a bounded below set. Let S subset of R be bounded below, then a real number L is said to be greatest lower bound of S if it satisfies the following conditions. First condition is L should be a lower bound of S, that is L should be less than or equal to X for every X inside S. That means every element of S is greater than or equal to L. And if M is any lower bound, of S, then L should be greater than or equal to M, right? Because L is the least, because L is the greatest of all the lower bounds. So relation between any other upper bound and L will be greater than or equal to M, right? So immediately we have this result. A bounded below set has a unique greatest lower bound. Okay. So the proof is very similar to the earlier one. Let S be a subset of R which is bounded below. So let L, M belongs to R be two greatest lower bounds of S. So since L is greatest lower bound and M is the lower bound, so the relation between them is L should be greater than or equal to M, right? Again, m is greatest lower bound and l is the lower bound, so m should be greater than or equal to l, right? So if you combine 1 and 2, then you will get l equal to m. So greatest lower bound of a bounded below set is also unique, right? So let us note this, that if S subset of R is non-empty, then there are four possibilities. S has both supremum and infimum. This happens when S is bounded, right? Just like closed interval 0, 1, it has both supremum and infimum. And another possibility is S has supremum but does not have an infimum, right? So that maybe interval minus infinity to 2, right? This has a supremum is 2, but it does not have any infimum, okay? It is not bounded below. Third condition is S has infimum but does not have supremum. So this happens when S is bounded below but not bounded above, right? And another fourth possibility is S has neither supremum nor infimum. Say suppose the set of rational numbers or set of irrational numbers, there is no upper bound, there is no lower bound, right? So these are unbounded sets. So let us now try to understand what is meant by saying that a set is not bounded above or not bounded below. Okay, this part is very important. How to deal with the negation. Okay, so for this we need some idea of quantifiers of mathematical logic. So basically these two quantifiers, the for all, that is for all or for every or given any, it is the universal quantifier, and there exist is the existential quantifier. So simple statements that we speak in everyday life can be written in terms of these quantifiers. For example, if I make the statement every student in this class is at least 5 feet tall, so mathematically we express it as height of student greater than or equal to 5 feet for every student in the class, right? So more rigorously we can say that h of x greater than or equal to 5 for every x inside S. Okay, so what is hx? Hx is the height of the student x, and S is the set of all students in the class. Okay, this is how we formalize the things mathematically. Okay, so consider the following figures and then observe the statement that follows, right? To understand this universal and existential thing, let us see what happens. So some figures are given to you here. So you see, and I make this statement, every figure here is a triangle, right? Every figure here is a triangle. So is it true or false? I'm sure everyone will say that it's false, right? Because here at least one figure is there which is not a triangle. Okay, I'm not saying it's a quadrilateral. Okay, all I need is at least one figure which is not a triangle. Okay, the figure could have been something like this also. Okay, so even then this statement is false. Every figure here is not a triangle. So at least one figure is there which is not a triangle. Okay, that is the thing. So immediately you will say that it is false. Why is it false? The argument given to justify falsehood will be no, there is a figure here which is not a triangle. Okay, so existence of one figure other than triangle is enough for justification. So mathematically we write this as there exists a figure that is not a triangle, or there exists x such that x is not a triangle. Okay, this is how we justify the negation. So then thus the opposite or the negation of for every is there exist, and the other way also, the negation of there exist will be for every. So consider the earlier statement, for every x belongs to S, h of x greater than or equal to 5. Okay, so what will be the negation of this statement? So if the statement every student is at least 5 feet tall is false, what does it mean? That it means that every student is at least 5 feet tall. I am saying that this is false. That means what? At least one student is there whose height is not less than at least one student is there whose height is less than 5 feet, not greater than or equal to 5 feet. Okay, so what should be the negation? Negation will be there exists an x inside S such that h of x is strictly less than 5. Okay, that is, there exists a student in the class whose height is not greater than or equal to 5 feet. Okay, so there may exist more than one student also, but existence of only one student which does not satisfy this criteria is enough to conclude that the statement is false, right? So this way we in general we may keep in mind the following: if the statement P is for every x something is satisfied, the negation of P will be there exists an x such that that particular thing is not satisfied. Okay, and the other way also it is true. It is both way implication. If P is this statement that there exists x for which something is not satisfied, the negation will be for every x that something is satisfied. Okay, so that way. So the reason for discussing these things is here. Let us have a look at the definition of the upper bound of that we had defined. U belongs to R is said to be an upper bound of S if x less than or equal to u for every x inside S. That is, every element of S is less than or equal to u. Right. So let us negate this statement. U belongs to R is not an upper bound if there is one element inside S which does not satisfy this particular condition. Right. So there exists, the negation will be there exists x belongs to S such that x is strictly greater than u. There is an element of x which is greater than u. That means u is not an upper bound. Okay. If u has to be an upper bound, then every element should be less than u. Okay. So if u is not an upper bound, that means at least there is one element which is greater than u. Okay, we need to understand this. So similarly, L belongs to R is said to be a lower bound of S if x is greater than or equal to L for all x inside S. So L is not a lower bound of S if there exists an element x inside S such that x is strictly less than L. Right. So using this concept, we have an equivalent definition of least upper bound and greatest lower bound. Suppose S is a subset of R which is bounded above, and U belongs to R is the least upper bound of S. Then what is the meaning? The meaning is no number less than U can be an upper bound of S. Nothing less than U can be an upper bound because U is the smallest of all the upper bounds, right? So we write this fact in a rigorous manner this way, that so any number less than u can be written as u minus some positive quantity, right? So for every epsilon greater than 0, u minus epsilon cannot be an upper bound of S. Okay, any number less than u can be written as u minus epsilon for some epsilon, right? So for every epsilon greater than 0, that u minus epsilon cannot be an upper bound. So cannot be an upper bound, that means what? There exists an element x inside S which is strictly greater than u minus epsilon. Okay, this is what just now I had explained, that u is not an upper bound. U is not an upper bound of S if there exists an element inside S which is strictly greater than u. So u minus epsilon is not an upper bound if there exists an x inside S such that x is greater than u minus epsilon. Right. So least upper bound can also be defined in the following way, equivalent definition. Let S subset of R be bounded above, then U belongs to R is said to be a least upper bound of S if it satisfies the following two conditions. U is an upper bound, first condition is same, and the second condition is for every epsilon greater than 0, there exists an x inside S such that x is strictly greater than U minus epsilon. Okay. So similar to this, for the greatest lower bound also we can have this type of definition. If L is the greatest lower bound of a bounded below set, then no number greater than L can be a lower bound of S. So for every epsilon, U plus epsilon cannot be a lower bound. So greatest lower bound is defined as, let S subset of R be bounded below, then L belongs to R is said to be greatest lower bound if it satisfies the following two conditions. L is a lower bound, first of all, x should be greater than or equal to L for every x inside S, and for every epsilon greater than 0, there exists an x inside S such that x is strictly less than u plus epsilon. There is at least one element for every epsilon which is strictly less than u plus epsilon. That means no number greater than u can be a lower bound. Okay, that is the concept. Okay, so another equivalent form can be observed. Okay, so if u equal to least upper bound of S, then no number less than u can be an upper bound. So if v is a number which is less than u, so v cannot be an upper bound. That means there is one element x inside S which is strictly greater than v. V cannot be an upper bound. So we also have this definition that S subset of R be bounded above, a number u belongs to R is said to be least upper bound of S if it satisfies u is an upper bound of S, first condition. The second condition is for every v less than u, for every real number which is strictly less than u, there exists a real number x inside S such that x is strictly greater than v. Okay, so we will use these definitions. Similarly, S subset of R is said to be bounded below if if S is a subset of R which is bounded below, then a number L belongs to R is said to be greatest lower bound of S if it satisfies the following two conditions. L is the lower bound of S, this is the first condition. The second condition is for every v greater than L, there exists one x in S such that x is strictly less than v. Okay, that way we can define. So let us use this concept to see what is the least upper bound of the closed interval 0, 1. So show that the least upper bound of closed interval 0, 1 is 1. So closed interval 0, 1 is the set of all those real numbers which lie between 0 and 1, including 0 and 1. So by definition 1 is an upper bound because every element here satisfies x less than or equal to 1. So 1 is an upper bound. First condition is satisfied. Now let v less than 1 be any real number. Okay. So what I have to show? I have to show that v cannot be an upper bound. So that means I have to find at least one element inside the set 0, 1 which is strictly greater than v. And then here in this particular case it's very obvious, if v is less than 1, then which element of the set satisfies which element x of this set satisfies x greater than v? The element 1 itself. Even the element the element 1 satisfies this particular condition. 1 belongs to 0, 1 satisfies the condition that 1 is strictly greater than v. Okay, so no number less than v can be a upper bound. Okay, that means 1 is the least upper bound. Okay, 1 is already an upper bound, and we have seen that no number less than 1 can be a upper bound. Okay, so 1 is the least upper bound, right? So it's very similar to this. Show that the least upper bound of open interval 0, 1 is 1. Okay, so in the earlier case you see that 1 is the least upper bound of this set, but 1 is also a member of this set. Okay, this makes the things little bit easier for us. But in the next case we have the open interval 0, 1, which is the set of all those real numbers which lie strictly between 0 and 1. Okay, so here x is less than 1 for every x inside 0, 1. So hence 1 is an upper bound. That's not a problem. Every element of this set is less than 1. So 1 is an upper bound. No problem. Now we take an element v which is we take a real number v which is less than 1. So it may happen that v is negative. So if v is negative, then every element of 0, 1 is greater than v, right? Because every element of 0, 1 is what? Positive. So whatever element you take from 0, 1, it will be always strictly greater than v, right? So in particular, say we take the element half. So we have got an element x equal to half which satisfies x is strictly greater than v, right? And another possibility is if v lies between 0 and 1, in that case half may not work, half may not serve our purpose. So what is our purpose? We need an element x inside the set 0, 1 which is strictly greater than v. So can we do that? If 0 less than v less than 1, okay, then you observe that there is a number between, there are actually infinitely many numbers between v and 1. In particular, the arithmetic mean of v and 1, that is v plus 1 by 2, it is a number which lies between v and 1, right? And v plus 1 by 2 is an element inside 0, 1, because v plus 1 by 2 is strictly less than 1. Okay, so the element v plus 1 by 2 belongs to 0, 1, satisfies v plus 1 by 2 is strictly greater than v. Okay, hence for every v less than 1, there exists an x inside S which satisfies x is strictly greater than v. Hence 1 is the least upper bound. Nothing less than 1 can be an upper bound. So 1 is the least upper bound of this set. Okay, so similar to this, let us try this one also. Show that the greatest lower bound of this set, greatest lower bound of the open interval AB is A. Okay, So A is equal to AB, open interval AB, it is the set of all those real numbers which lie strictly between A and B. So clearly x is greater than A for every x inside S. So therefore A is a lower bound of S, no doubt about that. Now let us consider, so I have to show that no number greater than A can be a lower bound. So let V belongs to R, be any number which is greater than A. So it may happen that V is greater than or equal to V. In that case, every element of AB is strictly less than V. Okay, that's not a problem. In particular, x equal to a plus b by 2 belongs to S, satisfies x strictly less than V. Okay, so if V lies between A and B, in that case, we take the arithmetic mean of this. We need an element which is less than V, so we will take the arithmetic mean of A and V, right? So let x equal to a plus v by 2. So we have a less than a plus v by 2 less than v. So x equal to a plus v by 2 is an element inside S, and it satisfies that x is strictly less than v. That means what? V cannot be a lower bound, okay, because there are elements which are smaller than v. So v cannot be a lower bound of this set. But what was v? V was an arbitrary element, arbitrary real number which was greater than a. That means no real number greater than a can be a lower bound of the set AB. That means A is the greatest lower bound. Hence, A is the greatest lower bound of AB. Okay. So, in particular, so the same proof will work for everything here. All this type of bounded intervals. So, least upper bound of closed interval AB. This is also B. Of right half open interval AB. This is also B. Left half open interval AB. That is also B. Open interval AB, the least upper bound is B. Least upper bound of minus infinity to A is A. Okay, similarly, greatest lower bound of AB, closed interval, is A. Greatest lower bound of right half open interval is the left endpoint. Greatest lower bound of the left half open interval is the left endpoint, right? Greatest lower bound of an open interval is the left endpoint. And greatest lower bound of A to infinity interval, open interval, is the left endpoint, right? So I hope you will you have got some idea about greatest lower bound and least upper bound. So there are some more properties. The very important property that can be derived from this least upper bound and greatest lower bound concepts. We will do in the next video. So in the next one we will discuss the completeness property of R, so which guarantees that every subset of R which is bounded above has a least upper bound in R. Okay, so whenever we have a bounded above set, its least upper bound will exist inside the set of real numbers. Okay, that is the completeness property of R, and we will discuss that in the next video.